Welcome to the Supply Chain Analytics course. This is Professor Panagiotis Drepousis, and this is the first part of the Distribution Logistics and Vehicle Routing Lecture 13. Distribution is often one of the most important parts of serving customers for every company. What is distribution? Distribution basically it is the management of materials and inventory that it moves through the supply chain from node to node. Therefore, distribution is the vital link through the supply chain, and managing distribution decisions and in general distribution logistics effectively, it is very crucial. On the other hand, it often represents a significant element of logistics cost for most companies, and it is often the most expensive function within the supply chain. Distribution is also important for another reason. It is also linked with the strategy that we have for the supply chain. In particular, it determines the responsiveness and effectiveness of supply chain, as well as determines the service level that we provide to our customers. Now, if we try to look at what are the figures of transportation of goods at the United States, we will say that it is estimated that US business, consumer and government spending on transportation represents something around 10% of the gross domestic product of the US. It is also estimated that this demand for freight transportation, it should be doubled in, let's say, 20 years from now in order to support the growth of the population as well as the economic growth of the United States. However, key question is how do we utilize the available resources and what is happening with the efficiency and the utilization levels. On the other hand, another important question is how do we maintain reliability over a large time horizon, and how do we plan effectively for the distribution functions that we have in the supply chain, not only in the short term but also in the long term. And third, another key point is what are the economic, environmental and societal aspects of distribution. Now, similar are the figures regarding the freight transportation within the European Union. And if someone tries to analyze whether the available resources are effectively utilized, we can see that a recent study showed that we have a 36% of empty driving. We have less than 60% of capacity utilization, while on the other hand, the logistics costs represented 7% of the total product costs. Therefore, it is evident that we can further reduce, there is a significant opportunity to reduce the logistics costs and improve to a large extent the utilization of the transportation resources. And with the term transportation resources, I mean not only the equipment and the vehicles and the trucks that we will use for the distribution, but also the available personnel that we have, as well as all supporting functions and activities that we have in the company and in the supply chain to support the distribution of our products. Let's try to define the distribution problem, and in particular the so-called vehicle routing problem. In most of the cases, we need to solve a problem where we have a set of customers, as shown here on the left-hand side of the slide. So these dots are customer locations. We have a fleet of vehicles, and we need to make some deliveries to deliver some products to these customer locations and to find a set of routes that minimize the transportation cost. So if we assume that this point here is the depot, is the point that all vehicle routes originate and they will terminate, on the right-hand side, you can see a possible solution of the vehicle routing problem. So if we follow with the different colors, the brown route, for example, this route here serves this group of customers, so that the vehicle will start its trip from the depot. It will start visiting customer along the route, and at some point it will terminate back to the depot. Key points here is to try to see what are the operational constraints that we have for this problem. For example, if the vehicles have a particular capacity, then we should ensure, for example, that the accumulated load, that the total demand of the customers for every route, they do not exceed this particular capacity. Or if we have, for example, a field service problem, where some technicians, for example, visit customer locations to provide the service to the customers, then we need to ensure that the total duration of the route, it will not exceed a predefined maximum level. Now, regarding the cost, how we can define the cost in a distribution problem like this one here, typically it has two components: a fixed cost that comes from using a vehicle plus some variable cost that is typically related with the distance traveled. So the longest the vehicle travels along a route, the greater will be the amount of money that we will spend for fuel, for serving the customer, for maintaining the customer, for maintaining the vehicle. Another question is, if we have this set of customers and we have a set of vehicles, how difficult is to solve the problem? If we look at the solution that I have here at this slide, maybe someone thinks that, okay, it doesn't seem so hard to find the assignment of customers to vehicles and to find the visiting sequence. Especially, someone may consider that experienced drivers, that they know their itineraries very well, they can be very good at drawing these solutions and coming up with heuristic solutions that they are very good. However, there are cases that drawing a solution, even if you have a few customers to serve, it can be very difficult. And if you look at the example that I have here, at the vehicle routing solution that I have here, it is apparently impossible for a human to come up with a solution for this particular problem. Here you can see a VRP solution with more than 80, 90 vehicle routes. So it is impossible by hand to try to find the vehicle routes. Now, if we try to understand what is the basic structure behind the vehicle routing problem, we can see that we can define these problems over a graph with the nodes and links. In particular, the nodes will represent the physical locations, for example, the location of our customers, or the location of a single or multiple depots that we may have in a solution, while the arcs, or links if you prefer, they will show the possible connections that we have between the depot and the customers, or between the customers, and they can also include the possible directions that we have available in order to travel from one node into another node of this graph. Now, of course, at the end, the number of arcs that they will appear in the final solution, they will determine the cost. And based on that, we can calculate also the distance, we can calculate also the travel time, and so on and so forth. Now, on the other hand, it is typical to know for each customer the quantity that it is required, or the demand, if you prefer, the cost to travel from and to every customer. While on the other hand, for the fleet of vehicles, typically we know the number of vehicles, or at least we have a maximum number of vehicles that we can utilize. And we also know the capacity of the vehicles, and this can be either the total weight, the total accumulated weight that we can load into a vehicle, or the total volume that a vehicle can carry. Now, in terms of decisions, typically we need to make two major decisions. We need to determine the assignment of customers to vehicles, or if you prefer, which customers each vehicle serves. And on the other hand, the second decision is to determine the visiting sequence, the visiting order of customers per vehicle route. What is the objective? The objective is to minimize the total transportation cost. Now, as I said earlier, the total transportation cost, it can be expressed either in terms of traveling distance or as traveling time. While on the other hand, we have to look at the structure of the distribution problem. Maybe we have delivery of products from the depot to the customers. Maybe we have pick-up of products at customer locations and return of these products to the depot. Or maybe we have a simultaneous pick-up and delivery of products at the customer location. So the vehicle is initially loaded at the depot with products, and along the route it deliver this product to the customers, while whenever the vehicle visits the customers, it also picks up return products from the customers and returns these products to the depot. So the first case here, delivery from the depot to the customers, this problem is called one-to-many. One is the depot and many are the customers. Pick up at customers and return to the depot. This problem is called many-to-one because we visit many customers to return the products to a single node of the graph, the depot in this case. And one-to-many-to-one is the third case where from one point, the depot, we distribute products to many customers, while from these many customers, from these locations, we also pick up products and we return these products to the depot. Now, regarding the objective function and the exact structure of the objective function, we also have cases that maybe we have multiple objectives that we can consider. For example, first to minimize the number of routes, and then to minimize the total distance traveled or the total traveling time. Maybe we have these two objectives in a hierarchical fashion. For example, first, the number of routes, to minimize the number of routes, and second, to minimize the total distance. But regardless of the hierarchy of 1, 2, or 3 or more objectives that we may have for a vehicle routing problem, in most of the cases, the typical objective is to minimize the total distance. While we always consider that a solution with fewer vehicles is better than a solution with more vehicles. However, it is important to notice that it is not necessary that a solution with a minimum number of routes, it will be a good solution with respect to the total distance traveled. In many cases, we will see that as we minimize the total number of vehicles, the total distance increases. On the other hand, there are also cases that the solution with the minimum number of routes, it is also the solution that we are able to find the minimum traveling distance. So we have to be careful. How do we use these two objectives? What is the relationship that we have between these two objectives, and how we are going to treat them? Now, in the real world, maybe we have, as I said earlier, a combination of time and distance objectives. However, it is also typical to include vehicle and/or staff-dependent costs, while in most of the cases, the number of vehicles that we have available for the distribution, it is also fixed. Now, if we want to summarize what we have said so far, a more formal, let's say, definition of we have the problem where in a given time period, we need to service a set of customers by a set of vehicles which are located in one or more depots. These vehicles, they are operated by a set of drivers, and all the movements, they are performed through a road network. As you can see here, I have grouped 6 main characteristics of the vehicle routing problem, and for each characteristic in the parentheses, I have the main attributes that we have that we typically need to consider. For example, regarding the time, maybe we have a single period problem or a multi-period problem, and we also need to see what is happening with respect to the duration of the route and the length of the route. On the other hand, regarding the customers, The parameters that we have for the set of customers is their demand. Maybe we have different types of customers. Maybe the customers, they need to be serviced within a particular time window, for example, between 10 o'clock in the evening until 12 o'clock in the evening. Maybe we have a service time. Maybe this service time is constant, or this service time varies with respect to the demand. And maybe all these attributes, they depend on the vehicle type, and we also have priorities or penalties associated with the partial service of the customer or the no service of the customer. On the other hand, regarding the vehicles, as I said earlier, maybe we have capacity restrictions. This is the most typical case. The capacity restrictions, maybe they have to do with the weight of the vehicle or the total volume that it can carry. Maybe the vehicle, the loading area of the vehicle is divided into one or more compartments. On the other hand, maybe we have also available devices, for example, loading and unloading devices, and maybe we have different costs because we have different types of vehicles. Now, regarding the depots, maybe we have one or more depots. This depends on the supply network that we have. Maybe we have different types of available vehicles in each depot. Maybe we have particular operating hours for each depot. And maybe also all the loading and unloading functions within the depot, they can perform within particular time windows. On the other hand, the vehicles that we have, they are operated by a set of drivers. It is typical that we need to follow particular DOT rules or union contracts or company regulations. And finally, all the movements that we have for the vehicles, they must be performed through a road network. In a real situation, the road network changes dynamically, the traffic changes dynamically, the traveling times from moving to one point to another, it is not a constant. In most of the cases, it is something that it is time dependent. So we also need to consider, whenever we try to solve a vehicle routing problem, to consider all these characteristics with respect to the time, with respect to the customers, with respect to the vehicles, the depots, the drivers, and the road network. Now, regarding the solution, what are we trying to find? We try to determine a set of routes, each performed by a vehicle that starts and ends at a depot, such that all the requirements of the customers are fulfilled. This can be the demand, or operational constraints are satisfied, for example, the operating hours of the depot, or accessibility restrictions between vehicles and customers, and we try to minimize the total transportation cost. And as I said earlier, this can be the distance traveled, it can have some fixed and variable costs. Maybe we want to minimize the number of vehicles or drivers. Another element that maybe we try to maintain or to minimize or to balance for a VRP solution is to balance the routes in terms of traveling time and vehicle load, so as to make sure that all drivers, they have equal workload. And at the end, maybe we have cases where we need to minimize some penalties associated with partial or no service. Now, if we want to depict some base cases for the vehicle routing problem, the most well-known problem in the literature is the so-called capacitated vehicle routing problem. In this case, the goal is find a set of minimum cost routes for a fleet originating and terminated at a single central depot in order to service a set of customers with known demand. So these are the customer locations, a single depot, we know the demand. So we have a case of deliveries of products from a depot. The fleet of vehicles is homogeneous. This means that all vehicles, they have the same carrying capacity. And we only have capacity constraints and route duration constraints. And this is how the solution looks like. Another very well-known problem setting is the so-called pick-up and delivery problem. Here, we need to find a set of routes for a fleet of vehicles in order to serve a set of transportation requests, as shown here in the figure, where each transportation request is defined with a pickup location and a delivery location. What are the basic constraints that we have for the pickup and delivery problem is that we visit exactly once each pickup and delivery stop. We do not exceed the capacity of the vehicles. We need to include in the same route both pickup and delivery nodes. And finally, we need to make sure that the visiting sequence, first we visit the pickup location and then we transport the products to the delivery location. And the solution of this problem maybe looks like that. So we have one route here. We pick up some products, we deliver these products, and then we visit another pickup location and we deliver these products. While the other route is a little bit more complicated. Initially, we pick up some products from this location. We pick up another set of products at this location, and we have one delivery stop here, one delivery stop here, and another pickup and delivery here, and the vehicle returns to the depot. Observe that we need to make sure that we never exceed the capacity of the vehicle during the vehicle route. So, for example, here we carry the products of these two customers as we travel this leg of the route. So we need to make sure that during this part of the route we do not exceed the capacity of the vehicle. And observe that all other restrictions that we mentioned, they are satisfied. So we always couple pickup and delivery stops, and we always make sure that the visiting precedence constraints, they are satisfied.